We already have seen that diffraction due to single slit and double slit. Now, if it is more than double slit, we can consider that, or we can treat that as n slits. So now we are going to see about diffraction due to n slits. N stands for some 1000 or 2000 or 10,000 slits. What happens if a light rays are incident on n number of slits, and what we are going to see on the screen, that we are going to discuss now. So let us say there are n number of slits. For space, there is a less space, so I am taking just a few number of slits only. So in general, we can take 1000, 10,000, 15,000, 30,000 slits also. So we are taking n number of slits of size E. So as usual, we are taking lens and we are keeping a screen. So by incidenting the light rays, a few of the light rays will passes through the gap of the slits and will focus at the center of the screen. Let us say this is P0. The center of the screen, and now the term E plus D, where D is the distance between two successive slits, the term E plus D is called a grating element. So as usual, so whenever the light rays are bent with some angle or they are diffracting at certain angle, and will focus at other point of the screen. So this point P1, whether P1 is bright or dark will depend on the path difference between two successive light rays. So in order to calculate the path difference, you have to plot a line, a perpendicular line from shortest one to the longest one, then we have to calculate the path difference. Now the path difference between any two successive light rays can be calculated as E plus D sin theta, already like similar to your double slit experiment. Remember, path difference between two successive slits. So you have to plot a perpendicular line from here to here. Since they are deviating with theta, so here the angle is theta and everything is like previous. So we can calculate the path difference between two successive slits is E plus D sin theta. From that path difference, we can calculate the phase difference. The phase difference phi can be calculated. You have to multiply path difference with 2 pi by lambda. So if you multiply the path difference with 2 pi by lambda, then you will get a phase difference phi. And let us say pi by lambda of E plus D sin theta as beta. So you can have phi equals to 2 beta. So since there are the resultant intensity or resultant amplitude on the screen due to single slit is given by A sin alpha by alpha. This is due to single slit. So like that, there are n number of slits. Due to n number of slits, the resultant amplitude on the screen, can be given as like this. R equals to A sin alpha by alpha into sin n beta by beta. It is similar to your double slit expression. Since the first term is due to the diffraction due to single slit, R equals to A sin alpha by alpha. Or first we take intensity, calculate the intensity I equals to R square, amplitude square of the amplitude will give you the intensity of A square sin square alpha by alpha square into sin square and beta by sin square beta. So this is the resultant intensity on the screen due to n, capital N number of slits. So now, the first term, this is diffraction due to single slit as we already discussed, and we know each and everything. The diffraction due to single slit graph is this one: principal maxima, minima, first secondary maxima, second secondary maxima. And now, if you take this particular term, this is the interference due to n slits. This is interference due to n number of slits, capital N number of slits. So this term, this term is giving a single slit diffraction, we know very well, and we discussed in particular and everything completely. But we don't know whether this is giving sin square n beta by sin square beta is giving interference pattern or not, we have to check. Now in intensity term, this is your intensity term. In intensity term, the first term will give you diffraction due to single slit, and the second term will give you the interference pattern due to n slits. So now, first take whether this is find out whether this is giving interference pattern or not. That means bright fringe condition and dark fringe condition or not. So if you take this particular one, call that as principal maxima, and now let this be as I dash. So the I dash is sine square n beta by sine square beta. In order to say this is maxima or maximum bright one, so this denominator should be 0. Because if it is 0, something by 0 is infinity, you are getting a maximum value of the function. So in order to have a maxima condition, sine beta should be 0. If sine beta is 0, beta equals to plus or minus m pi. So the value of m are 0, 1, 2, 3, 4 like that. If m is 0, beta is 0, sine 0, 0. If m is 1, pi, sine pi 0, like that you can have. So finally, the value of beta is pi by lambda of e plus d sine theta. So substitute the value of beta here, pi by lambda of e plus d sine theta equals to plus or minus m pi. So after cross multiplying lambda to that side and after pi will get cancelled, you can have e plus d of sine theta equals to plus or minus m lambda. Since e plus d sine theta is our path reference, means the path reference is m lambda. So if path reference is integral multiples of lambda, that will give you bright fringe condition in interference pattern. Similarly, find out the intensity of that principal maxima. So the intensity is nothing but I equals to a square sine square alpha by alpha square. But for principal maxima, you are substituting sine beta as 0. If you substitute sine beta as 0 here, then you will get infinity I value. We can't find the value. So then we have to go for L'Hospital's rule. So according to L'Hospital's rules, limit beta tends to m pi. Since we can't take in our regular textbooks it is beta tends to 0 or theta tends to 0, but here for every value of m pi it is becoming 0. That's why you have to take m pi. Sine n beta by sine beta should be equals to n, not infinity. If it tends to 0 or tends to m pi, it is n. So then instead of this you can take n, and if you square that one you can have n square. So the intensity of principal maxima is I equals to a square of sine square alpha by alpha square into n square with the help of L'Hospital's rule. So now your intensity, principal maxima intensity is directly proportional to n square, where n stands for number of slits. So if as the value of n is more, intensity is also more. So next, come for minima. So whether it is giving bright condition, come for minima. So for minima, in order to say this function or this my interference term is minimum, sine n beta should be 0. So for sine n beta is 0 means n beta equals to plus or minus m pi. So now the value of m is 0, 1, 2, 3 and so on, n minus 1, n plus 1 and so on like that. But here this is not taking all possible values, since m should not take 0. Why? If m is 0, put 0, n beta equals to 0 and beta equals to 0. So n beta is equals to 0 and then beta equals to 0. For beta equals to 0, if a beta is 0, you are getting principal maxima. So m should not take 0. Suppose m should also not take capital N also. Why? Let's see. If we take n, capital N, plus or minus n pi, n will get cancelled, then beta will become pi. So if beta is pi, if m is 1, then beta is pi. So beta is pi, again it's principal maxima. So m should not take n here. Similarly 2n, 3n and so on. Suppose if we take 2n, let's see what's happening. 2n. So if it is take 2n, nn will get cancelled, 2n pi, nn will get cancelled, then beta equals to 2 pi. For beta of 2 pi, you are getting, if beta m is 2 pi, beta is 2 pi, then you are getting principal maxima again. So here m should not take, or for m we should not allocate, or we should not give all possible values. So this is the condition. M should not take 0, n, 2n, 3n, 4n like that. So the minimum is, intensity of minimum is 0 because it is minimum. Now if you clearly observe that one, suppose I have n number of slits, n is 4, that means there are 4 slits. So if there are 4 slits, in between means your n is 4 here. So 1, 2, 3, 4. Suppose take the values here. The values of m will be, capital N is here, so 1, 2, 3, 4. We should not take 4. That means 1, 2, 3. All these are the number of minimas. That means there are 3 minimas are there. In between, for n, there are n minus 1 minimas are there. In between 2 principal maximas. Why? Because for n is 0, you are getting maxima. For m is 0, you are getting maxima. For m is n, also you are getting maxima. In between 2 maximas, we are having this many number of minimas. Suppose if my n is 4, there are n minus 1 minimas will be there. If my n is capital N is 4, my minimas will be 3. So in order to say there are 3 minimas, if one minima is there, it's uniform. If there are 3 minimas, that means in order to say this is minimum, there should be some maximum. In order to say this is minimum, there should be some maximum. So in order to say minimum value, there are some maximas will exist. So that means if my capital N is 4, this is principal maximas. In between 2 principal maximas, there are 3 minimas. 1, 2, 3 minimas are there. If there are, in order to say these 3 are minimas, there should be 2 secondary maximas. If there are 2 secondary maximas, then you can have 1, 2, 3 minimas. So in order to say there are 3 minimas, there should be n minus 2 maximas will be there. If n minus 1 minimas are there, there are n minus 2 secondary maximas are there, apart from principal maxima. So the conditions to have secondary maxima is tan n beta is equals to n tan beta. No need to, there is a large derivation. It's a qualitative treatment, so we can remember directly. The condition for secondary maxima is tan n beta is equals to n tan beta. Then if you simplify that one, the intensity of secondary maxima is n square by 1 plus of n square minus 1 of sin square beta, which is very less than the principal maxima. Suppose if this is principal maxima, the principal maxima is directly proportional to n square, the central one. But secondary maxima is n square by something which is less than the principal maxima. So your condition is I secondary is much less than I primary. Principal maxima, intensity of secondary maxima is very much less than the intensity of principal maxima. That's why while you are plotting, and these are principal maximas and these are secondary maximas. So the intensity of secondary maxima is much less than that one. Suppose if n values keep on increasing, here minimas domination will be there, more minimas will be there. Suppose if there are 1000 slits are there, there are 999 minimas are there. Since intensity of secondary maxima is less, so mostly it will appear like a dark one. Suppose if there are 30,000 slits are there are 29,999 minimas will be there. So automatically it becomes dark, only principal maximas will occur. So this is the term sin square beta. This is about sin square n beta by sin square beta. And this is a square sin square alpha by alpha square single slit diffraction. So if you see this one, the curve will be like this. It's curved like that. So on the screen, due to n number of slits, we can see only one image pattern. We cannot see single slit diffraction separately, and we cannot see interference due to n number of slits separately. Together they will form on the screen. So now this will come and overlap on this. like this. So these parts will get cut off, and finally see. You can have this. So this is your principal maxima, first order, second order. Principal maxima, first order, second order on right side and left side. So this is about your n number of slits. If you put n as the number of slits are increasing, the principal maxima brightness will increase. Because n square, principal maxima intensity is directly proportional to n square. You can have more intensity for principal maximas. But after overlapping this single slit diffraction term on interference pattern, then intensity of primary principal maximas will keep on decreasing on either sides. Only at center you can have a maximum intensity. If you keep on going, the principal maxima's intensity will keep on decreasing. There is no question of getting secondary maximas because they are having as the value of n square is increasing, here n square also there, automatically the intensity of secondary maxima will keep on vanish. So that's why you can't get a secondary maxima as the value of n is in terms of from 10,000s or 30,000s like that. So if you consider diffraction grating, it can be constructed with the help of by drawing lines, n number of lines on a glass plate. So if you take a glass plate and you have to draw n number of lines like this on a glass plate, you have to draw n number of lines with a diamond pointer, so that we can draw very thin and fine lines. So how many lines we have to draw? Per inch. Per inch means at the span of 2.54 centimeters you have to draw 15,000 lines. So per inch you have to draw 15,000 lines. With the help of a diamond pointer and a glass plate we can draw. So that we can obtain a diffraction grating. That means each and every line will act as an obstacle. So the gap between two obstacles is known as a slit. Like that we are having n number of slits. So per inch 15,000 lines means if there are 2 inches of grating is there are 30,000 lines will be there. If you take a small piece of glass plate and if you construct a grating by drawing the n number of lines, we can obtain around 30,000 slits on that small glass plate. Anyhow, for commercial purpose, they will give the impressions of or duplicate of the original one. They will never give you that original one. A duplicate they will take and they will keep that replica of that duplicate in between two glass plates and will give for students for practical purposes. And now this is about the construction of grating. Per inch you have to draw 15,000 lines. On an average, per 2 inches you can have 30,000 lines. So what happens here? And when a number of slits are there, since n is around 30,000, when light is incident on that one, you can have the orders. Suppose if a monochromatic light is incident, such as sodium vapor lamp is incident on a grating. So this is your grating. So what happens here? Principal maxima, first order, second order and third order. So this is principal maxima, first order on both sides, second order on both sides, third order on both sides. Since the principal maxima is having more intensity, first order is having less intensity than principal maxima, second order is having much less intensity than principal maxima, and like that, because of this diminishing curve. Principal maxima more intensity, first order, second order, third order. If we keep on going, the intensity will decrease. So one may get the doubt, what happens if a white light is incident on a grating? So on a grating, if you incident a white light, what's happening? Suppose if this is a grating and if I incident a white light on the screen, what we can observe? Here also same, we can observe a principal maxima which is having more intensity. And now in first order itself you have 7 colors will form, starting from violet to red. This is your first order. Even on the same both sides, the other side also you can have violet to red, first order. Violet to red, second order. violet to red, second order. So similarly, intensity of principal maxima is more. First order spectrum, violet to red, is having less intensity, and now second order is having less intensity than the first order. So like that on the screen, one can have a different WebGR colors in different orders. So with the help of spectrometer, one can view the colors and we can find out the angle of deviations with how much value we can the colors are deviated. And as the value of n is increasing, number of slits are increasing, this is having more brightness because I is intensity of principal maxima is directly proportional to square of the number of slits. So as the number of slits are increasing, the intensity of principal maxima will become more, and automatically this orders will keep on decreasing. As the value of order is increasing 1, 2, 3, 4, their intensities will keep on decrease on either sides. So this is a brief discussion or explanation about a grating.